Hello, this is Mr. Craig, and this is the second video for day 125 electrochemistry, more of the calculations part. Let's go ahead and get right to it. Example number 1, which of the following would be the best oxidizing agent? And from our choices we have chlorine, Cl2, iron metal, no charge, sodium, no charge, sodium ions with a +1 charge, and fluorine ions with a -1 charge. Now, the question also wants us to explain why this would be the best oxidizing agent. Now, hopefully we remember what oxidizing agents are or what they're doing. Now, if something is an oxidizing agent, it first must be reduced. So the thing that we want to look at is if it is a good thing that is being reduced, that means it's going to have a positive voltage when it is reduced. Now, again, what does reduction mean? It means that it's gaining electrons. So when we talk about an oxidizing agent, we're talking about something that is allowing for another substance to be oxidized while it itself is being reduced. All right, so let's get right to it. Looking at the first example, if something is being reduced, like in our case here with chlorine, what that means is it's going to gain electrons, and since there's two Cl's, and we know that chlorine wants to gain electrons, we have to find out what its voltage is. So from our standard reduction potential sheet, we come over and we look for chlorine, which is right here. It's the fourth one. And when chlorine is reduced, changing from chlorine gas to chlorine ions, it has a positive 1.36 voltage. So we're actually starting off pretty well here. So we have a positive 1.36 voltage. Now, the best oxidizing agent, or the best thing that's reduced, will have the highest voltage. All right, so let's take a look at the next example, iron. And again, this is solid iron. Now, does iron metal wish to be reduced? Now, ask yourself, what do metals want to do? Do they want to gain electrons, or do they wish to lose electrons? Well, if for some reason you're having a bad day and you can't remember, go to your standard reduction potential sheet and try to find iron that is a solid, and when it changes into a charge. So actually that's iron +3, so let's go down a little bit further. Here's solid iron, and changing into that, the only thing that I can see here is that iron metal is formed by a reduction of ions. So when we look at iron metal wants to have a positive charge. And hopefully you recognize or remember from at least general chem or from writing balanced equations earlier on in the year that iron likes to have a +2 or a +3 charge. The only way that iron's going to get a positive charge is by losing electrons, not by gaining electrons. So iron metal is out. All right, so looking at the next example, sodium. Hopefully you've learned something from the last example here, that if we're looking at sodium, sodium 2 is a metal, and sodium itself, from our reduction, when it's reduced, the only thing that we can do with sodium is, if it's an ion, reduce it. So since sodium is a metal, and we all know that sodium wants to have a +1 charge, it too cannot be reduced. Therefore, it's not going to make a good reducing agent. Oxidizing agent. It'll make a great reducing agent, but it will not make a good oxidizing agent. All right, so let's take a look at sodium +1. So sodium +1, this is a good thing. Sodium +1 can be reduced to form solid sodium, but let's take a look at the charge. So we still have that highlighted, and when sodium ions are reduced to form solid sodium, we have a -2.71 voltage. Well, a negative voltage is not something that is favorable. Now, based on the previous video, we showed that equation where we had delta G was equal to -N Faraday's constant times the voltage. If we have a negative voltage and we have a negative sign to start that off with, that's going to cause delta G to have a positive value. So for delta G to have a negative value, we have to have a positive voltage. So sodium ions are not a very good oxidizing agent because it produces a negative voltage. So we want to rule that out. All right, the last example, fluorine. with a -1 charge. Okay, well, we have a nonmetal here. Does or can fluorine become more negative? Well, we know that fluorine wants to have a -1 charge, but we don't know, or we know for a fact that fluorine never wants to be a -2 charge. Besides, there's no place to put that extra electron. It has 7 valence electrons. It wants one more. Taking on a second one just would not make sense. So when we look at fluorine, fluorine likes to be reduced, but since it's already a negative ion, it too will not be reduced any further to make a more negative charge. So there are two options here, the chlorine and the sodium +1, and we just ruled out the sodium +1 because it has a negative voltage. Therefore, the best oxidizing agent of these 5 would be chlorine, and that's actually chlorine gas. All right, example number 2. It says a piece of copper metal is placed into solutions containing each of the following 3 cations. Which ions will be reduced by the copper metal? So here's our scenario. We've got actually like 3 containers. Maybe this one has the 10 + 2. Here's another beaker that has zinc ions. And again, these are all solutions. Okay. And then we have a third beaker that has some silver ions in it. And when we look at that, what we're doing is we're placing copper metal in each of these. And the question's wanting to ask which of these will cause the reduction of the ion itself to form solid metal. So what we want to do here is we want to actually do the calculation to see if it is a spontaneous reaction. All right, so here's our diagram. Let's go ahead and get right to it. So we know that copper metal, again, since metal itself has no charge, and what's happening is it is being oxidized. We know that it's being oxidized because that's what metals wish to do. Now, we do have a dilemma here. Copper could be a +1 or a +2 charge, so we want to find the most favorable situation here. So when we come to our standard reduction potential sheet, we see that we have 2 coppers that are metals here. The copper +1 yields a positive voltage of 0.52 when it's reduced, and the copper +2 yields a positive 0.34 voltage when it's reduced. However, since we are oxidizing the copper, we want to go with the smaller value because it's a smaller negative value. So what's going to happen, nature will automatically make copper metal, when it is oxidized, a +2 charge because it yields a smaller negative voltage. Okay. Now, don't get excited that it has a negative voltage, because what we're looking at is the other thing to make sure that if this is going to be a spontaneous reaction, that the total voltage of this reaction is positive. So looking at the first one, the 10 + 2, well, let's go ahead and do that. We know that 10 would like to be reduced to take it from an ion to solid. So let's find out what that value is. So 10, let's find it, Sn + 2 going to solid right here. So when the 10 is reduced, it gives a negative 0.14 voltage. So the 10 ions will not be reduced by the copper in this reaction because it will yield a negative value, actually a -48. Okay, so the 10 + 2 will not be reduced when copper metal is placed into the solution. All right, let's look at the next example here. We already know we're going to go ahead and use the copper. I'm going to erase the 10. Okay, so ready? Erase that line too. All right, so let's look at the next example where we have zinc +2, and it will also be reduced to form solid zinc. So let's find out what that value is. Zinc. Where are you, zinc? And half of the fun with doing this is just being able to find these things. So here we go. Here's zinc that's being reduced. And when it's reduced, it also has a negative value. so negative 0.76. So that too will not yield a favorable voltage. So when we look at that, 1, 1. So a negative voltage there. So the zinc ions will not be reduced in this reaction either. Okay? And again, what we're trying to get is a positive voltage by all this. So hopefully in our last example here, using the silver, we'll get a favorable response here. So silver plus 1, when it's reduced, will form solid silver. And go to our standard reduction potential sheet. Silver's near the top. Here it is. Okay, so we get silver that has a 0.8, and that's a positive value for a reduction. So when we plug in the 0.8, and again, it doesn't have to be a large voltage, it just has to be positive. So when we take a look at this, we do have a positive voltage, which in this case I believe is 4.6 voltage. So to answer this question, the only thing that will be reduced by copper metal, and again, what's happening is the copper itself, metal, no charge, is turning into copper ions, and it's losing 2 electrons, and it's allowing the silver to gain those electrons. Now, this isn't a balanced equation. If we were to balance this, what we would need to do is multiply this by 2, stating that, okay, for this copper metal to lose 2 electrons and for the silver to gain those 2 electrons, we'd have to have twice as much copper. Now here's a really very important point. What we don't want to do is, since we have a multiplier of 2 here, we do not multiply this by 2. We never ever do that. The reason why we don't do that is because as long as we have silver and as long as we have copper, the reaction's going. This is what's called an intensive property. Intensive properties don't care, or it doesn't matter how much of the material we actually have, just as long as we have it. Now that's different from extensive properties, and I think I spoke about extensive and intensive properties earlier in the year. Here's an example of an extensive property. If I had a coffee cup amount of size of water and a swimming pool amount of water, which one would boil if I put a Bunsen burner under each one of those? Well, hopefully you'd say the coffee cup amount of water would boil first, because it has a smaller amount of water present. However, if I have that same coffee cup amount of water and that same amount of swimming pool water, and I ask you, okay, which one has a higher boiling point? Well, the boiling point's the same. That's an intensive property. As long as we have pure water, its boiling point will be the same, regardless of how much we have. So when we talk about intensive and extensive properties, voltage deals with an intensive property. As long as we have some silver and as long as we have some copper and this reaction's going forward, it doesn't matter how much silver we have. So if I need to have a multiplier of, say, 5 or 10 or whatever to balance this out, it doesn't matter, just as long as I have silver. So that's by definition an intensive property. That's why we would not multiply the amount of material that we have by the voltage. The voltage is set. Do not multiply it. All right. Let's look at the next example. Example number 3, it says, is the reaction spontaneous or non-spontaneous, and explain why, and then show all your work. All right, so we're looking at a single replacement reaction here, and the question's asking, will the lithium replace the copper in this reaction? So what we'll have is, we'll have lithium metal plus copper chloride, and if the lithium is capable of kicking the copper out, then we'll form lithium chloride. Now again, lithium has a +1, chlorine -1, and forming copper metal. So what we need to do is, first thing, let's find out the charges for each of these. Well, lithium by itself has no charge. Copper in this example has a +2 charge when it's hooked up with the chlorine, and the copper over here has no charge. So let's do the half reactions and do a voltage calculation. So let's start off with the lithium. Lithium, no charge, going to lithium +1 and losing 1 electron. Go to your standard reduction potential sheet, and lithium is near the bottom here. So lithium, when it is reduced, has a -3.05 voltage. However, Lithium is oxidized in this example, so we're going to use the 3.05, but as a positive value. So we have a positive 3.05 voltage, starting off well there. And then let's take a look at the copper, plus 2, going to solid copper. So we know that we have to gain 2 electrons for it to become neutral. So let's go ahead and look at our sheet again. I think we've used this in the last example. Copper, here we go. When copper plus 2 is changed into solid copper, it has a positive voltage of 0.34. So when it's reduced, and that's what's happening, a positive 0.34. So this is definitely going to happen. So we have a positive 39 voltage. So yes, this reaction most definitely will occur. Okay, now again, notice that we have 2 electrons here and just 1 here. The reason why I didn't balance the equation up here is because I want this to balance it for us. Notice that there's 1 chlorine over here and there's 2 over here, so I need to put a 2 there and a 2 there to balance out. And again, the half reactions do that for us. So if you forget to do that, that's okay. The half reactions should help us out in that regard. All right, let's look at part B. We have chlorine that's reacting with sodium fluoride. So let's go ahead and write that out. Chlorine plus sodium fluoride. Now, ask yourself this. Who is the chlorine trying to replace? Is it trying to replace the sodium, or is it trying to replace the fluorine? Chlorine is a non-metal. Chlorine will not ever replace a metal. So chlorine is trying to replace the fluorine here. Remember, in a single replacement reaction, the thing that stands by itself, whether it's a metal or a non-metal, will replace its own kind within the compound. So up above here, we had a metal, lithium, is going to replace the copper. We would not try to replace the chlorine in this case. Not going to happen. Okay. So what we want to, if we do, or if the chlorine is able to replace the fluorine, we would have sodium chloride, and we would form fluorine gas. Okay, and again, it's not balanced, but we'll go ahead and work from there. All right, so let's start off with the 1/2 reaction. Actually, what's going on there? So Cl2 going to chlorine ions. Since we have 2 there, that means we have to have 2 chlorines here. And again, be charge savvy, so make sure you have your charges on there. Since there's 2 chlorines and it goes from no charge to a -1, that means it's going to be reduced. So we want to look on our standard reduction potential sheet. Chlorine's the 4th one up there, and again, it has a voltage of 1.36. So that's starting off well. We have a positive 1.36 voltage. Okay, so now let's look at the fluorine. So the fluorine goes to fluorine negative goes to fluorine gas. Well, we need 2 of those. And if it has a negative charge, then that means that the fluorine is oxidized. Well, that can take place, but the question is, will that take place? So the very top here, we have fluorine gas that's reduced to make fluorine ions, and it has a positive 2.87 voltage as it's reduced. However, in our reaction, it is oxidized, so that means it has a negative 2.87 voltage, which means that this reaction has a negative voltage. So this one will not take place. No reaction. Okay. All right. Again, positive voltage means that it will be spontaneous. A negative voltage means that we have a positive delta G, which is not good. All right. Part C, magnesium reacting with silver bromide. So we have magnesium, no charge, silver bromide. And again, what's going to try to happen is the magnesium is going to try to replace who? The silver or the bromine? Well, magnesium is a metal, so it will try to replace the metal in this reaction. So it'll try to kick the silver out. So we form magnesium bromide. And again, magnesium has a +2 charge, so we need 2 bromines. And try to form pure silver. So if we have 2 over there, then that means we need 2 there. Okay, so let's find out if this will take place. So starting off with our first reaction, magnesium has no charge where it has a +2. Silver has a +1 where it has no charge over here. Alright, so magnesium no charge going to magnesium +2. How does it do that? Well, it loses 2 electrons, so it is oxidized. So let's get a value for that. Magnesium, there's manganese. Magnesium right here. When it's reduced, it has a negative 2.37, but it's being oxidized in this example, so a positive 2.37. And the silver, that has a +1 charge, going to solid silver, means that it is gaining an electron. Again, make sure the charges add up on both sides. So when we come over to silver, and that's near the top, it has a positive 0.8 voltage. So very positive here. So we have a positive, what is that, 3.17 voltage. So yes, this reaction will take place. Okay. So again, when we're looking at these types of half reactions, one will always be oxidized. The other will always be reduced. You can't have 2 oxidation reactions in the same problem. You can't have 2 reduction reactions in the same problem. So one thing has to be oxidized, the other has to be reduced. All right, last example here, and then I'll let you start on your homework here. Example number 4. Calculate the standard free energy change for the reaction shown below. Now, what wasn't given on your equation sheet is this conversion here where we have 1 coulomb is equal to a joule per volt. You do have Faraday's constant, which is on your equation sheet, and that's in coulombs per mole of electrons. And we'll talk about that here very shortly. When we talk about calculating the standard free energy change, we're actually looking for delta G. So the equation that we'll use for a problem like this is the negative N, and then we'll have Faraday's constant, and then your voltage. Now again, if we have a positive voltage, that means that that negative here is going to cause the delta G to be negative. That's what we want. We want a positive voltage, so we have a negative delta G. All right, the number of electrons will always be a positive value. Faraday's constant will always be a positive. So the determining factor is my voltage. All right, so let's take a look at our reaction here, and let's find out what our voltage is. So iron, which is a metal or a solid, changes into iron +2. So how does that take place? Well, that is an oxidation reaction. So let's find out what that value is. Iron +2. Where are you, iron? Did I pass you? Sorry guys, I can't find it. Here we go. So iron +2, and it has a, when it's reduced, it is a negative 0.44. In this example, it's oxidized, so it has a positive. Again, switch the sign if it's the equation spun around. So we have a positive voltage so far. Looking at our copper +2, and going to solid copper. Oops. So that means that it is gaining 2 electrons. And again, there's our copper +2. So copper +2 going to solid has a positive 0.34 voltage. So yes, we do have a positive voltage, which is very good. I believe that's a 0.78 voltage. All right, so now we can plug in our values here. How many total electrons? We're going to look at the end. How many total electrons are exchanged in this reaction? Well, the iron metal loses 2 electrons so that the copper ions can gain those 2 electrons. Since we don't have anything that we have to multiply by, let's just, for an example, say that this were a 3. Just for an example. Say that were a 3 and this were a 2. How many total electrons would need to be exchanged? Well, we'd have to multiply this top by 2 and this bottom by 3, which means that a total of 6 electrons would be exchanged. Well, in this example, there's only 2. So let's go right to it. So our delta G is equal to the negative number of electrons, so 2 moles of electrons. Faraday's constant, the F here is somewhere, I can scroll down, there we go, is 96,500, and that's coulombs per mole of electrons. And again, a coulomb is a joule per volt, and it's per mole of electrons. Okay, and then our voltage, our E here, is that value there, so the positive, scoot down just a little more, positive 0.78 volts. And let's type all that in. So I know I'm going to get a negative value here. And I come up with 1.5 times 10 to the 5th. And what's my units here? Moles of electrons are gone, volts are gone, left with joules. Now, if the question was just asking for the value for delta G, we'd be done. Now, if we needed to convert that into kilojoules, make sure that we know that we are dividing by 1,000 joules to make 1 kilojoule. So if the question was asking for delta G in kilojoules, then it'd be negative 1.51 times 10 to the 2 kilojoules. Alright, that should be enough to get you started on your homework. Hopefully this video has helped. If you have any questions, don't hesitate to email me.